Now, today's topic is quite important, to be honest, because during our control system design course, we have essentially three important topics to cover. Of course, all of them are important, but these are the fundamental parts of our course. One of them is the control system design using the time domain methods, which is exactly what we're covering now. And this poles, zeros, zeta, and omega n discussion today is going to be quite important about that fundamental part. And then there's frequency domain and state space domain. These are the other fundamental parts of our course. So today is going to be an important topic. And most of the discussion that we have today is going to be forming our basis on how to design a controller and how we evaluate the performance of a system. So yeah, it's quite important. So we will be looking at the behavior of a first order system. What happens to it if we, for example, move its pole? What will be the step response? What will be the impulse response? And then we will have the second order transfer function, which is the famous second order transfer function that we use all over the course. We have these parameters, theta and omega, and we will be talking about what they are and how we use them and how do they relate to the behavior of this system again for certain cases. Then we will be analyzing the case where we add a third pole or a zero to the system, how this will affect the system's behavior. And then we also have a part where we look at the setting time and rise time, but I'll be covering them just slightly, not entirely, because it's going to be available and it's kind of a task for you to remember and remind yourself how you can numerically acquire the formulas for these two time domain specifications. So let's dive into it. Let's start with a first order system. And let's see what happens. Let me define an omega vector here, omega n vec, which starts from 0.5 with 0.5 steps up to 2. So what I want to do is I want to just create also a figure here because I'm going to use this figure. Let's have a subplot where we basically plot one row. Let's have 3 columns. The first of that, CLA, hold on, grid on. Let's have X label time. So this is going to be the impulse response of the system. So Y label is going to be the output of the system. In this case, let's call the title the impulse response. And then we are going to have another one, which is going to be the step response of the system. What else do we have? And then let's have the pole spread of the system. So I'm going to remove this grid on here. This is going to be sigma. This is going to be j omega. So we're on the S domain. And this is going to be the pole spread. There we go. So let's give them some variables to handle them. So x1, x2, x3. Now I'm going to use again a for loop that will cycle through each element here. I'm going to call this omega n vec. This is going to be the ith element. Then I'm going to basically write the basic first order transfer function that we have at hand. Now, if I'm interested in the impulse response, what I can do is I can just call this yt for impulse and then grab the transfer function. If you remember from, I guess, the first or second week, we had something about this discussion here where we talked about the fact that LTI systems, when you add a derivative to the transfer function, you can easily acquire the impulse response. If you add an integrator, you would be transitioning to the ramp response. So let's just add that 1, 0, which is going to be S divided by 1 because we're interested in the impulse response. So I'm also going to define a vector, time vector, that looks like this. Let's say 10 seconds should be okay in my opinion. So I'm just going to ditch that and provide the time vector here. For the step response, of course, we can get rid of this, and it is just going to be GS. Now, for this system, I know where the pole location is going to be. Since it is S plus omega n, it should be at minus omega n. So what I can do is I can just plot the impulse response to the first one here, Y impulse, and then maybe assign it a color or line width better. There we go. Now AX2 for the step response. Plot AX3 minus omega n 0, because this is the real part. It doesn't have an imaginary part. I provide a 0 for that. Let's provide letter X for its marker and line width 2. And yeah, that should be actually it. If you're interested in the step response, impulse response, actually this should go away. And yeah. Let's run our script. And there we go. This is basically the response that we get. Now, obviously, we have some different colors for different cases. What we can do, we can just use the step response or the impulse response here to provide a display name to indicate which one is belonging to where. Let's have omega n and then num to str omega n. This will convert basically this will create a string that will remind us which one is actually which one. So let's have legend show. And there we go. Now we have a better view where we can see which color belongs to which one. But I'd like to change this a little bit more. I like to customize it a little bit more, where I basically create my own color gradients. You can provide a certain color in RGB to your plots in MATLAB by just using the keyword color and then providing the color. So I'm going to match everything's color like this. I believe this one should come before that, like this. And how are we going to path the color here? Well, we provide actually RGB values. And in most of the applications, it's RGBA, and we have 8-bit for each channel, which provides us a 32-bit structure or 4-byte structure. Here we're going to skip AS alpha. We have actually 24-bit data here, but then again, each channel is going to be a value between 0 and 1 in MATLAB. So when you provide something like 0, 0, 0, that would correspond to the color black. And if these are going to be 1, 1, 1, then you are creating the color white. You can basically mix the colors. And I'm going to do the exact same thing here, where I use the index here, because this index is going to be starting at 1. It will go up to length omega n vec. If I divide this into length omega n vec, in this case, let's have 5 elements. It would be 1 over 5, 2 over 5, up to 5 over 5, which would be then the full color. So it would start with a dark black color, and it would then gradients and transition into a light blue color. So then I would know that the starting point is going to be dark and the ending point is going to be a light blue color. So therefore, you don't really have to do this. I'm just going to implement it to visually try to assist the movements and to show what's really going on and which one belongs to which one. So let's have that. If we don't misspell anything, omega n vec should be better. There we go. This is basically the transition that I'm talking about. What I might like to do is to increase the marker here. And yeah, that's going to be it. Now, what we still can do, what we can add to this here in order to assist ourselves is the so-called zeta and omega n lines, which is basically something called S-grid, where you provide AX3, the graphics handle here, and then we have zeta and omega n or omega n vector. So we don't have any zeta value. Let's assume that that's 1. And we are going to provide this omega n vector here to the S-grid so that it creates us the following result. I'm not sure if it's visible or not, but here we have kind of circles or orbits where we have radiuses 0.5, 1, 1.5, and 2. In order to increase the readability, what I can do is I can just change the y limit here, or x limit, not y limit, of x3 to, I guess, minus 2.5 and then 0.5, so that we zoom out a little bit to see the whole picture here. So here we have the origin. This is kind of the S domain here, where this axis is going to be the j omega axis. This is the real axis, so real imaginary values. And we're on the real axis because it's a first order system. Its roots are only real values. So yeah, the basic assumption that we can make about the system's behavior is that when we move towards the left on the S domain, on the real axis, the system basically speeds up, or the system behaves faster and transitions faster from the transient state into its steady state. Now, we call the point where we enter the steady state, the time instance, we call that the settling time of a system. So basically, we have some percentages. Since this is the first order system, since we know the model of it, and it's quite easy to calculate it and obtain it, we know at which time instance we will get to basically 5% band or 2% band, which we never leave. And if that's the case, we just assume that the system is at steady state. It is at rest. So therefore, we can basically, for example, acquire the system's step response for first order system. If we are looking at the system's step response, what we can use is we can use the inverse Laplace transform, where we have basically omega n divided by s times s plus omega n. So that's more correct. And we can see that this is kind of the mathematical expression of our step response. And what we can do is we can just examine the exponential function here a little bit more, like this, for example. And let me assume that, let's plug in 0, for example, and then let's plug in -1. You can see that in one sample time, we reach the 63rd percent of our steady state value, which is quite impressive because it's a big step to take. And one sample more, and we're at 86%. One more step, and we're almost there. You can see we enter kind of this 5% band. Since we know from the step responses given here that the system doesn't overshoot, we can safely assume for 5% error band, the settling time is going to be calculated with minus t times omega n equals minus 5. Minus 3. There we go. Now the minus signs will go away like this, and this is basically settling time. So we get the settling time to be equal to 3 divided by omega n for 5% criteria. If we change it to 4, we can see that this is basically the 2% version of the same thing. So we can just write down 4 for the settling time for 2%. And yeah, therefore, when we remove this TS here, we can get Ts equals 4 divided by omega n. So if we're looking at a first order system, what we can do is we can basically safely assume that the pole will determine the settling time, and it relates to the settling time with 4 divided by omega n. Actually, this value is not exactly 4. If we plug in 3.91, that's going to be the exact point where we have 98%. So if we're looking at the settling time, if we calculate it experimentally or numerically from a certain given vector, we would see that it would be 3.91 to be exact. But we can use safely 4 because, well, it's not that important to have just 0.09 here, and it makes life easier. So yeah, we can safely assume that it is 4 divided by omega n. Now, rise time, peak time, and stuff like that for a first order system are kind of related with the same relation as the settling time is, because you can use the exponential term here and then analyze it and see how much time it takes to rise from 10% to 90%, or sometimes the definition changes from 0 to 100%. Then you can just basically use that for rise time. And well, giving a peak time here doesn't make that much sense because, well, the peak value is going to be the steady state value. So that's also another interesting topic. Those are more about the second order system, and you can use those formulas with zeta equals 1 for the first order system. So since there's no overshoot, we don't have any overshoot formula for this because it is directly equal to 0 if it's a first order system. So it's important to know this, that the systems model is an easy one, and we can just use the exponential term here in order to analyze it and then acquire the settling time. What we can still do is we can increase this, and I might prove it to you numerically that the settling time that I'm talking about does actually work. So let's have omega n vec in the x-axis and the settling time here, and call it settling time like this, and ax4. So what we can do is we can basically create an empty vector out of the omega n vector here. And somewhere down here, we can just get the step info of GS and then the settling time. The settling time of it, save it to TS vec I. And yeah, I could do something interesting here. I could still use the same gradient here. So let me just do it for once to show you how to do that. It's going to be AX4. I'm going to be plotting omega n versus TS vec. The color is going to be the same color, and line width property is also going to be the same. But here, what I have to do in order to create the same effect is going to be the following. I'll take I-1 and I, 2 points, 2 consecutive points out of these vectors here. And I'm basically referencing to the point that I've calculated now and the previous one. Due to MATLAB's property of indices starting with 1, I should be actually greater than 1 in order to be able to run such a code, because there's no such thing as omega n vec 0. You cannot access a zeroth element of a vector. So I should be greater than 1 if we want to have this same effect here. Yeah, let's see if this works. And as you can see, we now have also the same gradient effect that is here. So I'm going to remove this legend here, and I'm also going to remove this S grid here due to the following fact, actually. Let's also remove this legend show here, because I'm going to increase the gridding or the step size here. significantly to have a clear picture like this, for example. Now, obviously, we can see that we start with the dark one here at 0.5, and we go up to 2, and the system becomes faster and faster, because when we draw a 2% line from 98, you can see it enters earlier and earlier and earlier, and it becomes basically faster. Settling time is the amount of time which we have to wait so that the system settles down. Therefore, there's an inverse relation here. If we speed up, the amount of time that it takes to settle down is going to shrink or go down in value. So therefore, this is going to be an inverse relation here. Now, since this is an inverse relation, and since I've shown you that 3.91 is going to be the value that we're looking at, maybe I could just use omega NVEC and also 3.91 element-wise division omega NVEC, and then we need a certain color. Yeah, let's use black, for example, and I'm going to just choose a huge line width. And you can see now, actually, you can't see the previous experimental data where we had the settling time versus omega NVEC calculated with step info, but you can see it is on top of it because, well, obviously we cannot see the plot underneath of this plot here. So we might want to do this before we have that, and maybe a certain red color to hopefully be visible. So that's kind of it, but I don't know if the gradient is visible, but yeah, you get the idea. We can see that 3.91 does actually give us the settling time. So this is important in the sense that when we have the settling time relation, when we know that we can choose basically omega NVEC or the omega n value, or actually the pole of the system, so that it has a certain settling time, we can reverse this process. Someone can give us the settling time requirement, and we could come up with a pole that satisfies that, and then we start to look at stuff from the design point of view. Another fact about the first order system, since we don't have any overshoot in its step response, its impulse response becomes never negative, because the integral of the impulse response will give us the step response. And at some point, if we would have a negative value in the impulse response, that would mean that we should subtract from the general integral sum, which doesn't happen here because we don't pass the line 1 here, so the steady state value. Therefore, the integral never decreases. And of course, the step response is also always increasing, and it'll just settle down. It will just stop here. It never decreases because we don't have overshoot. If we would have had some overshoot, we would pass this line, and at this point we need to decrease to come back to our value which we are going to settle down. So that's the reason why we have no negative part in our impulse response, which is also quite important to notice. So this is basically the maximum analysis that I think we can make about a first order system, because it has not that much capabilities. It has only its settling time. It doesn't overshoot. When we go to the left on the S domain on the real axis, it speeds up, and that's basically first order systems summarized. So what we can do now is kind of use the same strategy in order to analyze, for example, a second order system, which should be more important in this case. Let me just create another figure. Now we don't actually have the impulse. We don't have to look at the impulse response. So I'm going to get rid of that. Let's have 2, 3. We have again the same time vector. And let's get rid of this. x1, x2, x3. Now, let's see what the specifications are. Let's choose omega n equals 1. Omega n equals 1. And we are going to vary between 0 and 1. This is going to be zeta vec now. So therefore, everything that is going to use basically a vector, the for loop itself, length omega n vec here, those are going to be versus zeta vec here, probably this one too. So this is going to be the value of zeta, omega n, ts, zeta vec. Yeah, this is going to be zeta vec. And let me actually hide this setting time for now, because that's going to be interesting. So, of course, this does change. And these are also going to change, but yeah, let's see. Now, the model is going to be omega n squared 2 times zeta times omega n s plus omega n squared, because that's a generic second order transfer function that we write down. So no impulse response, just the step response plotted, and that's going to be it now. And this is going to be something else, so I'm going to calculate that now. Now, for those who don't know how to handle zeta and omega n, I'm exactly going to cover that now. So let's write down the actual polynomial. That's going to be plus omega n squared equals 0. Now, what we can do is we can look at the solution of this second order equation that we have, or second order polynomial, which is quite easy because we could use the formulas given for a generic second order polynomial. So we know that the solution is going to be minus b plus minus square root of delta divided by 2a, like this. So what is b? That's basically 2 times zeta omega n. Let's write that down. What is delta? Delta is going to be b squared minus 4 times 1 times omega n squared. And 2a, since a is going to be equal to 1, becomes only 2. So let's work on this a little bit more. We can see that that becomes 4 zeta squared omega n squared minus 4 omega n squared. And let's factor out 4 omega n squared. We end up in getting zeta squared minus 1. Since we have the square root here, we can just pull this 4n squared out as 2 omega n. And we can see that the coefficient omega 2 vanishes here, since we have these coefficients 2 here. Now, this is basically a solution that we could be happy with, but another small trick that I'm going to use here is I'm going to revert this into 1 minus zeta squared to have a 1i here, so that this part becomes the imaginary part, this part becomes the real part of our solution. Since if delta squared, or delta in this case, is positive, we will have real roots, real distinct roots. If delta is exactly equal to 1, we will have coinciding roots. And if delta is negative, which I assume at this point, we will have basically imaginary complex roots, actually complex roots, complex conjugate roots here. Now, this is going to be the imaginary part. We sometimes call this omega d for damped frequency, and we call this part sigma, which is the real part, so that we show it like sigma plus minus j omega d in order to define the complex conjugate pair. Now, this is basically the solution of a second order polynomial, and therefore these are the roots of a second order transfer function that we write down and use as the notation most of the time. So yeah, since this is the solution, we can actually look at certain aspects of our solution, like the magnitude. Now, since this is going to be it, we can just take the real part, its square, plus the imaginary part, take the square, like this. Now, this would be omega n squared, and the square root vanishes. And if we distribute omega n squared, we would end up in this. Whereas this one here is basically zeta squared omega n squared. Now we can see that this multiplication is basically the same as omega n squared zeta squared. So they will cancel each other out and we will be left with omega n squared. If you're looking at the absolute value, you should also have the square root. I didn't write it down because it's obvious that we have that. So the square root of this or the square root of this, which is basically going to be omega n. So this shows us that the magnitude s is going to be omega n. Now sigma squared plus omega d squared is equal to omega n squared. So what this means is that on the s domain, we have basically a circle with radius omega n. So and the center of the circle is, of course, the origin, because sigma minus 0 and omega d minus 0. So it's going to be centered at 0, 0, and the radius is going to be omega n. So we have kind of this circle, this omega n circle at the origin. So that's one thing. Since we're at it, let's look at the argument, which is another property in polar coordinates. And that would be then a tan d imaginary part, and then divided by real part, which is zeta times omega n. Now you can see that omega n again cancels out. We get rid of that. And then we end up in this, which is going to be called theta. Now, if you look close, we have the square root of 1 minus zeta squared, and then there's also zeta. And this is actually a triangle. And if we work out what the hypotenuse is, you would end up in 1, because the square root of 1 minus zeta squared is going to be 1 minus zeta squared plus zeta squared will give you basically 1. And therefore, what you can do is you can write down what cosine theta is, and that's going to be this portion divided by the hypotenuse, which is 1, so it's going to be zeta. So what you can do is you can work out what zeta is, because you might want to use the angle of your solution, the argument of s basically, which is theta, take the inverse tangent and then take the cosine. Let's call this cosine d, because d stands for degrees. And yeah, you can calculate what zeta is. And if you think about it, when we fix omega n, you get a circle at the origin with a radius omega n. And if we fix zeta, we fix theta to a certain angle, and that's actually a line on the s domain. So that's the reason why in a moment we will see that zeta is going to form some lines and omega n is going to form some circles, and their intersection is going to define our pole pair. So that's important to know. If you look at the s domain, you most of the time think about the Cartesian coordinates, the real part, the imaginary part, and that's it. That's not it, actually. We have a certain zeta line, and we have a certain omega n orbit, and when they collide, when they intersect, we have basically a complex conjugate pair. And it is important to know that because when we are designing it, we will be looking at a certain zeta value, and that's going to be crossed by the root locus plot, for example. And then we'll see if it's possible to design a certain controller or not. So it is important to know this polar coordinate stuff about the poles of this system. Yeah, These are basically the analytics about the second order polynomial or the second order system that we write down most of the time. Now, let's get to numerical stuff here. For this reason, when we have this, we are going to define sigma as minus zeta times omega n, and then omega d as square root of 1 minus zeta squared times omega n. There we go. When I'm going to plot it, it's going to be sigma, comma, omega d, and also its conjugate minus omega d, because this is the imaginary axis, this is the real axis. I'm going to have two poles for this system. Now, we can also display this the zeta and omega n lines. I'm going to give it the zeta vector and omega n value, and it should basically show us the zeta and omega n lines. Let me actually fill out the setting time vector here like this. And let's run the second script. Yeah, x1, x2, x3. There we go. So now you can see that actually we have a half circle here. Again, I'm going to zoom out a little bit here. So x lim of x2 minus 1.2, 0.2, just a little adjustment to see the whole circle here. Now, we can see that we have just one half circle with radius 1, because that was omega n. We defined omega n equals 1. That means that the absolute value of s should stay 1. This is going to be the circle that we're working on, or this is our orbit. Now, since we're changing the zeta values, for each iteration, we get a different zeta value. Therefore, we get basically a different angle, because remember that cosine theta is going to be zeta. So the inverse cosine of zeta is going to give us a certain angle. Since we are talking about cosine, if this is 90 degrees, cosine 90 degrees is going to be 0. I actually need to zoom out a little bit more in the y-axis here. Let's make it 1.2. So now we can also see the zeta values. Since I've used S-grid here, it will display the zeta vector values and the omega n values that are provided. So I can see that here we have zeta equals 0. That 1 belongs to actually the radius of omega n here. The zeta value here is 0, and the theta, so the angle here is going to be 90 degrees. Now, we can see that this is kind of the darkest pole pair here in terms of color. So it means that we have a sine wave, a perfect sine wave that oscillates forever. Now, when we're talking about zeta, by definition, zeta is called the damping ratio, and omega n is called the natural frequency. And here I actually did write down the damped frequency because it has the damping ratio times the natural frequency. So it's called damped frequency. And it kind of determines the behavior of the system. And if we want to associate the behavior here that we see on the left with the one on the right here, with zeta, we can easily do it. And if we think about a pendulum, that would maybe help us out, because the friction for the pendulum is zeta for the damping ratio, and it kind of acts like a pendulum if you think about it. Now let's think about frictionless pendulums. When you release them from a certain height, they will just basically go down, and the kinetic energy or the potential energy is going to be converted into kinetic energy. It has an equilibrium point of like straight down, but it would take some energy consumption, or the friction should do some work in order to have a energy loss in the system so that it'll settle down. But if there's no friction, the potential energy is going to be converted into kinetic one and then back again to potential energy, and this will go on forever, and it will oscillate forever. Since there's no friction, it will oscillate forever and ever and ever. When we introduce slight friction, a little bit of friction, it would actually lose some energy on its way. So what this would cause then is basically a loss of energy. Therefore, when it goes through the equilibrium point for the first time, it has lost already some energy, so it will not be able to rise that high up because it doesn't have that energy now. So therefore, it will have basically kind of this behavior here where we can see it just needs, or the height is not that high, and it will just being damped down. So what I can do probably in order to increase the visual effect here, I could just increase the time here. You can see the oscillations go forever. But other than that, we can see that everything settles down, but it takes some time. And since the friction is low, it just goes high, and then from the equilibrium point a little bit there. But essentially what it does is it tries to settle down, and it does eventually. Now, if you increase the damping ratio or the friction in the system, this will become basically faster, because the faster it loses the energy, the faster it will settle down. Then there comes a certain time or a certain zeta value that corresponds to the ideal path for the pendulum to stop at its first pass. What I mean by that is we release the pendulum and it goes down, and it exactly stops at that equilibrium point and doesn't pass through it a second time because it doesn't need to. So the amount of friction that is needed to basically run out of energy is called the critical damp solution, and that's zeta equals 1 in our system. And you can see here that the response of such a system is the brightest blue here, and it goes up and it settles down. It never passes through the same point twice. So that's zero overshoot behavior, which we had in the first order system. That's called here critical damp. Of course, we stop at this value here, so therefore we don't see what happens if we increase it furthermore. And we'll analyze that in a moment. But let me bring up the settling time back. So let's have the settling time here. We have zeta vec, we have TS vec, and yeah, let me try this. So you can see it seems like it works a bit different, but it's not actually. This will correct itself in a moment. For these systems, for a second order system, we actually know what the settling time is going to look like. And in Ogata's book, I guess, this book which has a black cover, The Modern Control Engineering was its name, I guess. In that book, you can see the proofs of settling time, rise time, peak time, etc. All the formulas that we might use in the upcoming weeks. They are present there. I highly suggest you to check them out because they're quite explanatory. As far as I remember, the proof of the settling time was about the real part of the poles, about sigma. And the sigma part on its own is necessary to model the settling time, not the sinusoidal parts, not the oscillation parts. And the reason for that is the following. When you have the exponent term -4, for example, times lots of sinusoidal waves, it doesn't really matter because you will multiply them with 0.0498 or 0.05, which will basically get rid of the whole sinusoidal part anyways. So if it's -4, it's going to be 0.0183. So therefore, what it does is it just takes the real part of the poles, which is sigma, which is zeta times omega n, and uses that to model the settling time of a second order transfer function, which is seemingly the same as for the first order system. So you get basically -4 equals minus zeta times omega n. Zeta omega n -4 is going to be the value there. So therefore, it is just going to be TS. So we have TS here. So it's going to be 4 divided by zeta omega n and nothing else, where zeta times omega n is kind of the absolute value of the real part of our pole pair. And I can just demonstrate to you that when I go down here and multiply omega n with zeta back here. Hope that it will be obvious. Now, first of all, let's convert back to that. With omega n, zeta back. What is the issue here? Oh, x4. That's not x4. It's going to be x3. Here we need omega n in order to be exactly correct here. So this doesn't seem like it matches the settling time values, but I'm going to again remove the S grid here, which was exactly here. And I'm going to increase the amount of points that we look at. And you can see now it does actually match the settling time values, even though it does match the settling time line. So the model kind of works. We can see that at the end, we have some nonlinearities about this formula here. When we are at high zeta values, I guess, or when we have a system that is quite fast, then we get some nonlinearities, but it doesn't really matter in terms of design and analysis because a little error can be made. So that's not that big of a deal. So therefore, we will not, we will just go ahead and use this model that we have here. But note that for zeta equals 1, yeah, exactly. For zeta equals 1, the value doesn't really match the model that we have here. And exactly here somewhere, 0.9 is going to be where the model has some differences and it will not catch back up. So yeah, but we're happy with the formula that we have here. So that's going to be used for a second order transfer function. Since we don't really want to use zeta equals exactly 1, if we have a certain overshoot in our mind, we're just looking somewhere on this line here. So we're okay with the settling time formula that we have here. Of course, we will have a overshoot formula too, but that's not going to be today's topic. But there's a formula and you can look it up if you really, really want that. So here we can see how smooth the transitioning is from sinusoidal waves into this first order kind of behavior. And yeah, now what we can do is we can see what really happens if zeta is greater than 1. For those solutions, we call them overdamped systems because in the pendulum example, if you think about it, the friction is actually too much at this point. And the system slows down, the pendulum slows down due to friction because, well, it takes more time to get there. It will eventually stop at that point, no matter what, but it takes more and more time if you increase zeta. So let's actually plot that too. Let's maybe create the same plot here. Let's call it 3. But now we will use zeta vec 1 up to 2. And yeah, that should be actually it. 1, 2. There we go. Now, first of all, the problem is that our solution is not this anymore. So why? Because we violated the fact that 1 minus zeta squared should be positive, and zeta should be less than or at least equal to 1. But that's not the case here. Now, what we could do is we could just use this as the inverse of it. So zeta squared minus 1. And instead of doing this, what we can do is we could add or subtract this, because now we assume that this is going to be the real part. And we will not have an imaginary part because overdamped solutions have real distinct roots. Therefore, the imaginary part is going to be 0. So we kind of fixed that. Now we know that the formula doesn't work for overdamped systems. As you can see from this figure here, it doesn't work. So why calculate it? It's just not working. So let's get rid of that. Now we can see the settling time here is shown here, and it does increase, and the system becomes slower and slower. Now I need to, I guess, also get rid of this for a moment. There we go, that makes more sense. Now, arguably, we're actually seeing a first order system behavior because there's no overshoot, and the more we go to the left, supposedly, or actually, we're actually also going to the right, but this one is kind of dominating the behavior. It seems like we become slower and slower, which aligns with the fact that this part is dominant. We see that the settling time increases, the amount of time that we have to wait increases, the system becomes slower. Now, this is actually an interesting system, and most of the time we don't use overdamped systems for design purposes. And the reason is the following. You have one pole that goes towards, or that just approaches the j omega axis or the origin, and we have another pole that kind of goes to the left. So one pole becomes a faster and faster pole on its own, and the other one is becoming slower and slower. So you have this imbalance where one of the poles is becoming slower and the other one is becoming faster. So at some point, this part here loses its meaning because this is becoming faster. For example, if you have like 2 here, 4 divided by 2, if this would have been a system on its own, would be 2 seconds of settling time. Whereas we can see we have a settling time of 10, 14 seconds here. So for 2 seconds, the fastest one is going to settle down, and we will just have the slow part here. So that's the reason why you actually have this kind of interesting behavior where almost all responses start the same, but then become slower. Because this one here becomes active and it becomes slower and slower. Why would I bother with a system that looks like this to design a certain system? Because in the future, we will see that this high change of rate here is also nothing that we want in control system design. So this is not an ideal system. We don't have a settling time formula exactly for this, or not quite that handy. Like 4 divided by zeta times omega n. So that doesn't work. We don't have any overshoot. So yeah, therefore we don't really use this for design purposes. If it's between 0 and 1, if the zeta value is between 0 and 1, then we can have some overshoot and a certain settling time, or any of the 2 time domain specifications like peak time, rise time, overshoot, settling time. And we can then come up with this zeta and omega n pair, where we base our choice so that we have a certain omega n circle and then zeta lines, and we're trying to choose these points for designing a certain system. Now, let's look at the second order system, but Now we are going to change basically omega n. At this point, omega n was fixed, and we've changed the damping ratio, and we've seen that these systems actually, the behavior of these systems are decided by the zeta value. Now let's see what happens if we change omega n. Let's fix zeta for 1 or 0.5, and let's vary omega n and see what is going to be the result. So let's have 4 and 5, I guess. There we go. And I'm going to just comment this part out and start with this one here. Now, I don't believe that I need 30 seconds here. So now zeta is going to be equal to 1, but we will have omega n vec, and the vector starts from 0.5 up to 4. 0.5 up to 4. Omega n vec. Now I think I've established the fact that the setting time formula is a certain formula. So I'm not going to demonstrate it over and over again. Yeah, so let's get rid of this part here and this part also. There we go. Now, zeta is equal to 1, omega n vec is this value here. The loop should be based on that. We should use omega n here. The coloring should be based on omega n vec. The same system, the same roots, step response, whatever the poles are going to be. And I might want to open this one up. This is going to be zeta. This is going to be omega n vec. And let's get rid of that. So let's first analyze this one here. From 3. Now, again, we have basically this first order system behavior. Because zeta is equal to 1, we have a critical damped system. And yeah, if we increase the radius of omega n, or omega n for short, then we see that we are going to the left. Therefore, the brightest one is the fastest one. The darkest one is going to be the slowest system. So the system speeds up, but the behavior stays the same. It's just a speeded up version of it and nothing else. So what we can do is we can just copy and paste this stuff here for figure 5. Like that. And change the value with like 0.5. Let's see what happens now. Now we can see that instead of being on the real axis, we have fixed zeta. And when we fix zeta, we're basically talking about constant cosine or constant zeta values. So these are all the same. These have all the same zeta values here. And we have also the symmetric one here because they will be conjugates. And then we have these omega n orbits. Since we're changing only omega n, we are kind of landing on a different orbit here for each system. Now, the interesting fact about this is the following. We have basically all the peak values aligned. So that means that the peak value doesn't change, and peak value transitions into overshoot because peak minus the value in steady state divided by the value in steady state times 100 gives us the overshoot percentage, and that wouldn't change if we have the same peak value, and we do. So certain zeta values will correspond to certain peak values, which will give us basically certain overshoot values. And I'm just going to increase the sampling a little bit more in order to have a better view. So yeah, let me get rid of S-grid again. And let me increase this to 0.01 and 0.01. There we go. Now we can see that here the behavior doesn't change. It's almost a 3D graphic now, where it is just shifted. And this is also the reason why we call these omega n values the natural frequencies, because the frequency is only changing, but the shape of the response stays constant. Now, I could choose a maybe more dramatic one, like 0.25. And here on the right, we can see the shape is kind of the same, but you can see it is shifted. So it looks like a three-dimensional thing that we can look at probably, but the behavior will always be the same since it's just shifted with omega n, or it is stretched out with omega n, and that's basically it. Now you can see that MATLAB kind of adapts its own axes and stuff. So even though these seem to be the same, of course they are not, because the axes are different here. The scaling is different. You can see that this stops at -1, whereas this stops at -2. So you should take that into consideration. And if we want to, what we can do is we can maybe copy the, since this is the greater value, I guess, we could copy the x limit of, I don't know, maybe from 5 to 4 or vice versa. So figure 5. Let's set the y limit. Oh, we're actually losing it here. X4. So let's call this 3, 3. Oh no, this should be X3. This should be X4. The y limit of X4 should be the y limit of X, I guess, 2. If that makes sense. So let's call it 0.25. Let's make it 0.5. Not the y limit, actually, the x limit, I guess. So. Yeah, now you can see I've copied the x limits here. They should be the same. Since the y limits are also the same, you can see that this is a lower zeta value, this is a higher zeta value. The behavior is also therefore a bit different, but we can see that this is kind of the shape of the behavior, and omega n just stretches out it in terms of frequency and nothing else. So yeah. Again, since we're going towards the left, it will never change, because if omega n increases and if zeta is going to be fixed, we will be going to the left, and it will become faster and faster and faster. And that's going to be basically it. So it is quite important at this point to summarize this. If zeta is going to be between 0 and 1, then the system behavior is decided by the zeta parameter here. And omega n is just going to be a frequency stretch of that shape and behavior. If we are between 0 and 1, we have certain formulas for settling time, rise time, peak time. Even though I didn't cover all of them, you should have them in your notes, and it would make sense because they will only depend on zeta and omega n and nothing else. If it's between 1 and 2, we have too much friction, too high of a damping ratio. Therefore, the behavior is not quite what we want. It behaves like a first order system anyways, and we don't really have formulas for design. So we would rather stick with this one here. If we want 0 overshoot, then we just choose zeta equals 1. But other than that, most of the time we will be lying between 0 and 1 for zeta. And zeta corresponds to peak value and also therefore overshoot. If we have a certain overshoot in our mind, we will see that in the upcoming weeks. There will be a formula between zeta and overshoot. We will just calculate what zeta is going to be. And then we will use settling time or another time domain specification parameter, and then calculate maybe omega n, a circle with radius omega n at the center of the origin or in the S domain. and two lines which are symmetric going to intersect with this omega n circle, and we will get our solution for the second order system. Now, up to this point, we've talked about the first order system, the second order system. We did tweak some values and see what is going to be the result looking like. Now, at this point, it is even more important than the previous part, because here we're adding a third pole. And if I'm not wrong, last week we designed a p-type controller using the algebraic method. I've introduced you to the algebraic method and the p-type controller design, and we had a third order system. Now, up to this point, zeta and omega n is just defined for the second order system, and omega n could be basically also used for a first order system. But what happens if we have a third order system, or more specifically, if we add a third pole to the second order system, or if we add a zero to the second order system without touching the gain of the system? You see p divided by s plus p. The reason for that is that it doesn't affect the system's overall gain in the steady state, because this on its own has gain 1. If you plug in s equals 0, you will see p divided by p is just going to be 1, which goes also for the 0. So that has gain 1. We're just adding the pole or 0, and we don't affect basically the system's gain. So now let's actually create the system where we have fixed omega n and zeta values, which means that this system's behavior is going to be fixed in terms of peak value, in terms of settling time, in terms of behavior. Everything is going to be fixed. And what we're going to do is we're going to add a pole in a certain different interval and another one, and see what is going to be the result. So let's create run 4. This is going to be 6, I guess, and this is going to be 7 or whatever. So zeta is that, omega n is also the same, but now we have something called pvec, and everything will be varying based on that. That's going to be called p omega n vec. I'm just going to maybe get rid of this and copy paste the one before that. So let's have pvec. Yeah. So we'll have another pole, and these will be fixed. So I'm going to give them a fixed red color. And this is exactly at minus p and nothing else. Minus p comma 0. Because I'm adding a real pole. Because I can just add a real pole if it's just a single pole. Now the transfer function is going to be multiplied with actually 1 divided by, or p divided by s plus p. So zeta omega n seems to be right. The pvec interval was 2 and 10 and 0.1 and 0.5. Let's take 0.1 and 0.5. Yeah. Seems to be all right. Run 4. But we need a little bit more time. Good to know. Let's make it, for example, 30 seconds. Run 4. There we go. Now, what do we see here? First of all, these red pole pair, or this red pole pair here, is going to be, it is actually calculated with the zeta value, with a certain zeta value 0.5, and we are on the orbit 0.5. So that's that. So this is our original second order system. What we do is we add the pole in the vicinity, basically, and we see that at some point, and when we add it at 0.1, for example, it behaves like a first order system even. It doesn't have that overshoot or the peak value. And when it goes to the left, it kind of starts to look like a second order system response. But yeah, we cannot conclude anything about this. The only thing is that we basically have a third order system. It behaves on its own. It has its own characteristics, and that's it. So maybe when we add it in a different interval, let's call it figure 7. Second interval was 2 and 10. Let's have 2 and 10. And yeah, nothing else changes, I guess. Let's run that. Here, the behavior is a bit different. Now, when we look at this one here, we are in the vicinity of our zeta omega n pair, or our dominant pole pair, which we will call it. And here we are out of that region, and we are far away on the left. I have told you something in the lines of when we have a pole that is too fast, it will have a certain settling time. For example, if we have the pole 8, for example, 4 divided by 8 should give us 0.5 seconds. In this 0.5 seconds, the effect of this pole is going to be settling down. Then we are left with the zeta omega n pair, which I guess has real part 0.25 or something on those lines. So it means that it would be, if it's 0.25, it would take 16 seconds to settle down. And that's exactly what the system behavior looks like. So this whole thing here is actually sufficiently fast so that in the first couple of seconds, we actually get rid of these effects of the third pole, and the overall system almost always behaves like the second order portion of it. Whereas here, that's not the case. I can, by the way, increase that also a little bit more to have a better view. Maybe we should get rid of that. And let's run it again. Here you can see the behavior does change when the pole moves, and we cannot assume that they have a certain settling time or a certain overshoot because it changes with the pole. But here the pole has slight effects on the system's behavior. So when we calculate all the settling times, overshoots, rise times, since the shape of the system does also not vary that much, I don't say that it doesn't vary at all, but it doesn't vary that much. So that's the keyword here. So we can kind of assume that we are okay with that. We have a certain settling time, we have a certain peak value or overshoot, and this whole family here shares almost exactly the values for the second order system on its own. So it seems like when we add a pole that is far away from our pole pair or a second order system, our ideal system, the overall system behaves like a second order system. And this farness, or how far the pole is kind of always set like 5 times or 6 times away from the real value of our dominant one is sufficient. So if this is -1, if the real value of our dominant poles is going to be -1, you should be at least at -5, -6, at least. -10 is even better. And from that on, it doesn't care, because compared to each other, their relative speed is going to be not that important, or their effect will be minimal, and we could use this. So it goes on like this when you add more and more poles. The only restriction is that it should be their real value, or their minimum real value, or the closest one's real value should be at least 5 times away than the dominant pole pair. Then the dominant pole pair will dominate the behavior. So it's quite important to know this, because we can add some poles, we can have some higher order systems, but we can still treat them like second order systems if we are lucky to end up having the third pole far away. That was the case last week, where we had like a 11 time factor, I guess, something along those lines, where K was 198, and then we had P at 11 on our real value of our dominant poles were like -1. So we had this nice behavior, and we matched our setting time requirement of 4 seconds last week for the p-type controller. This is the reason why, because if it's far away, the third pole doesn't really affect the system. But if it enters the zone, if it enters the dominant region, which is this region here, then it affects the system's behavior in terms of settling time, overshoot, everything changes. Here, almost nothing changes, just numerical differences, which makes sense, because in the real world, we will not have exactly 4 seconds of settling time and exactly 10% of overshoot, because that is nonsense. So therefore, higher order systems can be controlled with this strategy, which is called dominant pole placement. These red ones are going to be the dominant poles that we call them, and the other ones are going to be pushed away. And we hope that the overall system behaves like a second order system, because we have tools for it. We have setting times, all sorts of stuff for second order systems, and we apply this to higher order systems with this dominant pole placement strategy. Let me quickly copy run 4 and rename it to run 5, and just invert the transfer function here. I'm going to be a lazy person now. I'm not going to rename everything to 0. I'm just going to treat this as if it were a 0, because I've just inverted it. It should be an effect of 0. I should at least convert the representation to a 0 representation, but that should be it. And this should be 8 and 9, I guess. Yeah, I should run 5, I guess. There we go. Now what we see here is that in case of adding a 0 in the dominant region, in the vicinity of our pole pair, is a bit more dangerous than adding a pole, because at least the pole was dominating for some portion, and we had 0 overshoot, and then it just changed the system behavior, but it didn't surpass the overshoot of the pole pair. But here we can see that's not the case. Here we have a like 350% overshoot, something like that. So it is way worse than adding a pole to the system. So if we have a 0, then we might end up in a very bad system response, and also even higher overshoot values and all that stuff, which is not nice at all. But for most of the systems, you as the designer of the controller is going to be adding the 0 to the system, because if the system doesn't have a 0, the controllers will have, for example, if you're designing a PI controller, the PI controller has its 0, and you're the one on deciding on the location of the 0. So if it's in the vicinity, that's your fault. That's going to be your fault. So yeah, that's not actually that nice to know about systems, because if we add 0s, we will be we need to push them away, but if they're far away, they will not have that much effect. So it's kind of an interesting relation there, because you want to add 0s, but you're not really able to do that in terms of dominant pole placements. Yeah, it's going to be a dilemma. So yeah, but it is what it is. On the other hand, if it's far away, again, if these dominant poles are exactly dominant, then the system behavior again doesn't change that much. So if you add poles, if you add zeros, it doesn't matter. If you have decided on two of them, all the other poles or zeros should be pushed away so that the system behavior is going to be the one that you expect. Because otherwise, if they're entering the zone, if you're entering the dominant region, they will mess up your system's behavior in terms of shape, in terms of specifications, in terms of everything almost. So keep that in mind. This was basically an explanation for last week on how we did design the p-type controller, because all we knew was the second order part of the system, but we hoped for the best and we ended up in a dominant pole assignments result that was usable. Of course, it was picked carefully, so that's the reason why. But yeah. Now, in terms of the importance of this is that for higher order systems, for PI controllers, for PD controllers, for PID controllers, or for all other classical controllers, this is kind of the way of designing them if you're looking for reference tracking. The method is called dominant pole placement. You're just deciding based on zeta and omega n, or actually based on settling time overshoot or time domain specifications. You decide on zeta and omega n. That forms your pole pair. You decide on two of the poles. All the remaining poles need to be pushed away, and you look for, if you have more than one solutions, you look for the best in terms of dominance. If not, then you have just one choice and you go with it, or you change maybe your controller. In real life, the time domain specifications for settling time and overshoot, even if they depend on the application, is mostly on you. You might want to relax your time domain specifications a little bit, then the system turns out to be maybe a more dominant one, and then you will be successfully designing a controller. Or if you just have too tight conditions, that might be forcing the system to behave which it cannot behave like. So yeah, you as the designer should start to design and look for a certain controller, but then you might readjust your time domain specifications, which changes everything, where you should basically go from scratch, but it's an iteration. So yeah. This was actually what I wanted to talk about: zeros, poles, zeta, and omega n. But we have this last portion here, so let me show you and recap the whole lecture of today. I want to show you this piece too. Now, we looked at the first order system. This was kind of the behavior of a first order system. We talked about the non-negativeness of its impulse response, non-overshooting property of its step response, and if the magnitude of the pole grows or increases, the settling time decreases, the system becomes faster. On the S domain, this corresponds to orbits or circles with radiuses omega n. And we can see that when we go towards left, it will become faster. Now, then we analyzed a second order system, and we've seen that for a parameter called zeta, which is the damping ratio, if it's between 0 and 1, then the whole shape, the behavior of the system is kind of decided by this parameter. And we gave the example where we have this pendulum, and the friction in this pendulum system corresponds to the damping ratio zeta, and you see all the possible different outcomes of a system step response if zeta is between 0 and 1. If it's 0, it's on the marginal stability, and its frequency is calculated directly by omega n. So it's going to be a sine omega nt, because there's no damping ratio, there's no damping, so it's going to be a sine wave. Other than that, if you increase zeta, you will get to a certain point which is called critical damp, and that's where the potential energy of the pendulum is going to be consumed by friction, and you will stop at your equilibrium point in one go, basically. If the damping ratio is greater than 1, we call the systems overdamped. And well, those systems are not really the ones that we look at, because the even the omega n radius loses its meaning because one of the poles tends to the origin, the other one is tending to the left on the S domain, and we have this weird combination of fast and slow poles, which kind of messes up the whole idea here, and it doesn't have overshoot. So why would we use it? We could maybe go with the critical damped, and that's the best we can do here. If you fix zeta, you fix basically the behavior of the system. And if you vary omega n, the best it can do is stretches out the step response. And yeah, it's kind of for adjusting the speed of the system, but nothing else. The shape stays and remains the same. Yeah. Then we actually, this is for some other parameter, I guess, zeta is equal to 2, and then we do the same for that. Now, if we add a certain pole in the dominant region, then we see that the shape changes, all the specifications, all the properties changes. So in this case, we cannot use this type of setup for controller design for a third order system if the third pole enters the dominant region. But if it's far away out of the dominant region, then we can see that the effect is minor on the step response. We can assume that the overshoot and setting time values, rise time, peak time, whatever, they're kind of the same and similar. So we can use this for controller design purposes. We can hope for the best dominance factor in terms of poles, and it should work like butter. Now, what about adding a 0? Well, the effects are almost the same, but even worse for the dominant pole, dominant region zeros. If they are entering the region, then your shape is messed up, but your overshoot is also very, very, very high. And for that reason, you should be careful about zeros. But then again, you're the one who is going to add the zeros to the system. So it's kind of a dilemma. But other than that, it doesn't matter if it's a 0 or a pole. If it's far away, we don't care about it. And that's also something nice because it should be far away and we're good with it. So what you can do for time domain specifications is the following. You can use MATLAB's fit function and fit type function in combination in order to generate these approximate formulas for setting time, rise time. What we do here is we have an iteration. We just try some different omega n values, get the settling time, put that in a table. One column is going to be omega n values, the other column is going to be settling times, and then we provide the fit type. So we're kind of giving it the model. So this defines the whole model of our settling time formula, where a divided by x is going to be the formula here, because we're looking for coefficient a, where our relation to x is going to be 1 divided by x. So we give it the fit here, and it just creates us the results in terms of divided by zeta omega n. We can do the same for rise time and settling time for a second order system, and you might want to try this out. Just fill a table of zeta omega n columns and a column for settling time and another column for rise time, so that you can provide them individually to the fit type function and the fit function here in order to see what the settling time is, what the rise time is in terms of zeta and omega n for a second order system. So you can see for the first order system, it's 3.9121. For the second order system, it seems like 3.79 is the exact value that MATLAB came up with. Here we have a second order system, and we can see that the rise time here is approximately modeled with this given formula here, whereas the second order version is also available here. So we will use them for design purposes, and there might be sometimes some problems that will ask you for rise time is going to be 2 seconds, settling time is going to be, let's say, 6 seconds. Design me a controller that has these properties, or design a controller that ends up in a closed loop that has these properties. Then what you have to do is you have to work out 4 divided by zeta omega n, and this formula, for example, you should solve them simultaneously to be able to retrieve what zeta and omega n should be. because that's the only aim here that we are going to have. Because once you have zeta and omega n, you can determine where the assignment should take place, and everything is going to be obvious from that point on. But other than that, these formulas are just used to retrieve zeta and omega n. That should be a rule of thumb. Well, that's it basically for this week. Hope that you that this was helpful for you. And let me also remind you that we will be starting to having quizzes, and in the YouTube channel's I guess community tab, I have a choice for the day of the quizzes, because they will be simultaneous with the other class. So please vote there so that we decide on the day, and then we will start having some quizzes. Of course, all quizzes will be announced, so there's no surprise factor. Yeah, that's it basically. If you have any questions, feel free to ask. I'll try my best. Other than that, we'll see each other next week, same day, same hour.